And yeah, and we have to do hybridization of carbon over here. Okay, we have to do hybridization of carbon. So central atom is carbon. So write first the configuration of carbon, which is 1s2, 2s2, and 2p2. Correct? But you know that the valency of carbon is 4. So it should have 4 unpaired electrons. If you write the ground state configuration, we have discussed that 1s never goes for any bond formation because it is very close to the nucleus. So we'll 2s, this is 2s, and then this is 2p. Then we'll draw its excited state, 2s and 2p, like this. Like this. Okay, so if you put electrons like 2s2 and 2p2, so it has only 2 unpaired electrons. So in the excited state of carbon, 1 electron from 2s, jumps into 2p.
Yes, sir.
And once done, you can say that carbon will have 4 unpaired electrons, which it should have because its valency is 4. Got it?
Yes, sir.
Now 1s orbital overlaps with 2p orbital to form sp2 hybridization. This hybridization is called sp2. Why sp2? Because 1s orbital overlaps with 2p orbital to form sp2 hybridization. And when the sp2 hybridization is there, I am drawing the hybrid state now. See, drawing the hybrid state. The hybrid state will have 3 orbitals, and each one of them will be called as sp2. Why 3 orbitals? Because 1s orbital and 2p orbitals are there. So it becomes 3 hybrid orbitals. This is HO. HO means hybrid orbital. Okay. Now look at the diagram. The diagram will be little tricky. 3 hybrid orbitals of first carbon. See, this is first carbon. First carbon ka first orbital. Then at an angle of 120 degree, second, at an angle of 120 degree, third orbital, third hybrid orbital. Okay. Now there are 2 carbon atoms in C2H4. So the second carbon atom will also undergo sp2 hybridization. It will also have a triangular planar shape like this. So now I have drawn single bond between the 2 carbon atoms. Now what I will do is I will put 1 hydrogen over here, 1 over here, 1 over here, and 1 over here. Okay, because there are 4 hydrogen atoms. So 4 hydrogen atoms means 4 electrons are present. Now, if you see this orbital, can I say that this orbital, which I am highlighting it with, say, pink color, this orbital, it is unhybrid orbital. Can we say that?
Yes.
Because it is not going for hybridization. See, it is not under that red color highlights, shape. So unhybrid orbitals, they always form pi bonds. So there will be one unhybrid orbital like this of the first carbon atom. Similarly, the second carbon atom will also have one hybrid orbital, and the type of overlapping between them will be parallel overlapping. So parallel overlapping means what kind of bond is formed in parallel overlapping?
Parallel overlapping, pi bond.
Very good. So the orange orbitals, they will form pi bonds. And the bond angle in a triangular planar geometry is 120 degrees. The geometry is the same. That is triangular plane. So just draw this C2H4. So just remember this, wherever there is a double bond of carbon, wherever there is one double bond of a carbon, its hybridization will be sp2. If you remember this shortcut, you don't have to do this entire, working. If there is a double bond in carbon, and if that carbon is having only one double bond, then by default, hybridization will be sp2 only.
Carbon,
Sorry.
if there is carbon double bond, it's sp2. Yeah.
If matlab, see, I will give you one example. Suppose if they ask you this one. See, look at the screen now. Suppose if they ask you this one. Suppose if they ask you this one, that give the hybridization of these two carbons which are highlighted with orange color. Okay. So can I say both the carbons are having double bond? One
Yes.
double bond.
Yes.
Okay, the condition is it should have only one double bond, not more than one. If it is more than one, something else will happen that we will discuss in next 10 minutes. But right now, that two carbon atoms are having only one double bond. So the hybridization for both of them, okay, for both of them, it will be sp2. So this will be sp2 as well as this one. But what about the carbons which are highlighted with green color now? Are they having any double bond?
No.
So they are having single bond. So again, a golden rule. If all the carbon atoms are having single bonds, if the carbon atoms are having, one minute, if the carbon atoms are having only single bonds, if the carbon atoms are having only single bonds, then their hybridization will be sp3. So very simple to remember this. If carbon is having single bond, it is sp3. If it is having a double bond, it will be sp2. And after some time, I will teach you that if it is having a triple bond, it will be sp hybridization. Got it, madam?
Yes.
Okay. Just copy down this thing and let me know once it is done. Then, madam?
1 second, sir. Yes, sir. Done.
Right? Okay. Now look at this. See, I will be stopping the screen share for a moment. I will try to see if my video gets on. Yeah, I'm lucky. See, no, I'm not lucky. It got off again. पता नहीं ये ऑटोमेटिकली ऑफ हो जाता है मेरा वीडियो. एक मिनट रुको, आई विल ट्राई अगेन. You can see this. If you carefully check this, see, these two are the carbon atoms. Okay, and can you see a double bond between them? See, these
Yes.
two bonds.
Yes.
Okay, and the four hydrogens are, see, 1, 2, 3, and 4. So now when I say that bond angle is 120 degree, where is that 120 degree? See, this is the first bond. Okay. Out of these two bonds, you can take any one bond and consider it as a linear bond, like this, a sleeping line. You can consider any one. And then this third bond. So if you see that thing, it will look somewhat like this. See, it will look somewhat like this. You will have one bond over here like this, one over here and one over here. So this angle will be 120 degrees. Now you agree with me how the bond angle is 120 degrees? Yes?
Yes. Yes.
Okay. Okay. So this is how alkenes are formed. The alkenes, the speciality of alkenes is that they have a double bond. Last time, I had shown you methane ka structure.
Mm.
So it was tetrahedral. It was three-dimensional. This is two-dimensional. This is a triangular shape.
Mm.
Got it? Like this bond and this bond, they are in the same plane.
Yes.
Such a thing was not happening in methane. In methane, one bond was going out of the plane
Yes.
because it was a three-dimensional geometry.
Mm.
Right? Here only three bonds are there, and all of them are at 120 degree. You can look at the, it's just like three blades of a fan. So the measure of a circle is 360. So the angle between any two blades of a fan will be 120 degree, and similarly in trigonal plane. So what is the shortcut that I have told you? See, if the carbon is having all single bonds, as I had shown you last time, like this, if all the carbons are having single bonds, then it will be sp3 hybridization, and the geometry will be a tetrahedral. If the carbon is having one double bond, see this one, then its hybridization will be sp2, and the geometry will be trigonal planar. The bond angle will be 120 degree, whereas the bond angle in tetrahedral between any two bonds, you take any two bonds, okay, any two bonds you take, the bond angle will be 109 degree and 28 degree. Got it? So they ask you in MCQs the bond angle in sp3 hybridization is, or they will ask you the bond angle in methane is. So how would you come to know what is the bond angle in methane? So first you need to find the hybridization of methane, which is sp3. Then you will say that since it is sp3, obviously it will be 109 degree and 28 minutes. Similarly, if they ask you for ethene, so you need to know that in ethene there is a double bond. So the hybridization of carbon will be sp2, and hence its bond angle will be 120 degree. Got it?
Yes, sir.
Of course, madam. See, hybridization, what topic we are doing since our last lecture now, is the most important topic of this chapter. Very important topic. Along with, there is one more topic towards the end we will do, which is called molecular orbital theory. These two are very, very, very important topics for your NEET exam. And all these concepts will help you in your entire inorganic chemistry.
Yes, sir.
Okay? So don't by heart the things. If you want to by heart it, but understand and then by heart it. Okay? Just blindly don't by heart it, because if they twist something, if they twist the question, then we might go. But if our concepts are clear, if we have understood what is this sp3, what is this sp2, what kind of hybridization are present in this molecule, then even if they twist the question, it will be becoming very easy for us. Got it, madam?
Yes, sir.
So after this sp2 hybridization, the next hybridization that we have to do, the next hybridization that we have to do is of ethyne. But before ethyne, we'll do it for BeCl. Okay, we'll do it for BeCl. It is called beryllium dichloride. Okay, so what happens in beryllium dichloride is just look at this entire thing properly. In beryllium dichloride, who will be the central atom? Can you tell me?
Beryllium.
Beryllium, perfect. So beryllium will become 1s2 and 2s2. So according to valence bond theory, its valency is 0 because it does not have any unpaired electron. But in reality, the valency of beryllium is 2. So which means that it will have to go into an excited state because the ground state does not have any unpaired electrons. So let me just draw the ground state. Ground state will be 1s2 and 2s2. But as I told you, 2s2 will only participate in bond formation. 1s never participates in any bond formation. Since it is very close to the nucleus, it has a lot of attraction towards the nucleus, and hence it does not participate in any chemical bonding. So
Yes.
what happens in excited state is one of the electrons of 2s jump into 2p, because after 2s you have 2p structure. 2p. So this is 2p. Okay. So one of the electrons jumps over here. Got it? So now what will happen is, see, this is our 2s and this is our 2p. So now it is very simple. You will say that, sir, one s orbital will overlap with one p orbital, and this is going to give rise to what hybridization? This is going to give rise to sp hybridization. Why sp hybridization? Because one s orbital overlaps with one p orbital, and hence it is sp hybridization. Now remember this, we had written this in our last session also, that whenever it is sp hybridization, can you check your notes and tell me what was the shape that we had done, or what was the geometry we had done if it is a sp hybridization?
Speed hybridization is like linear.
It's written on the screen. If the hybridization is sp, then the geometry will be linear, correct? Its structure will be linear. Are you able to see on the screen, madam?
Yes, sir.
So now it will be of a linear geometry. Okay. So linear geometry, how are you going to draw the linear geometry? There are two hybrid orbitals. So first we'll draw the hybrid orbitals over here. So in hybrid orbitals, there are only two orbitals. Two hybrid orbitals. Okay. So this is like 1 and 1, two hybrid orbitals, because only two atomic orbitals are overlapping. And the valence bond theory says that the number of hybrid orbitals, or I would say that the theory of hybridization says that the number of hybrid orbitals are always equal to number of overlapping atomic orbitals. So since two atomic orbitals are overlapping, two hybrid orbitals will be obtained. And when two hybrid orbitals have to be arranged in space, obviously the angle between them will be 180 degrees. Okay. Just give me 1 minute. Someone is calling. So 180 degrees is the bond angle in linear geometry. So say this is the first hybrid orbital. Okay. And remember this, during hybridization, like if this is one orbital, say this is upper lobe and this is lower lobe, then we say that the lobe which goes for bond formation gets automatically expanded, and the lobe which does not go for bond formation, which does not go for overlapping, will be squeezed out. Why? Because if the orbital or the lobe which is going for overlapping is bigger in area, is larger in area, then the extent of overlapping will be more. And remember, in our last lecture we had done that during VBT, the extent of overlapping decides the strength of the bond. So if we want a stronger bond, the overlapping, the extent of overlapping should be more. And if the lobe which is going for bond formation, which is going for overlapping, has a larger area, then obviously the extent of overlapping will be more. Okay. So for example, this is just an example. If this orbital which is white, if this lobe which is colored is going for extent of overlapping, is going for overlapping, then it automatically expands its area, and the lower lobe, which does not go for any bond formation, is squeezed up like this. So here there will be overlap.
Yeah.
Got it, madam?
Yes, sir.
Okay. So only one of the lobes is expanded and the other lobe is squeezed up. So for example, this orbital is going for, or this lobe is going for overlapping. So it gets expanded, and this orbital or this lobe, I would say, does not go for any extent of overlapping. So it is squeezed up, it is compressed. Now similarly, the other hybrid orbital like this, the other hybrid orbital, this first, and this, it's that lobe which does not go for bond formation. And now you will have two chlorine atoms, and since chlorine is also a p block element, so it will bring p block, p orbital. So this lobe will be expanded and this will be squeezed up. Similarly, in another chlorine, this lobe, sorry, will be expanded. So here there is a single bond, physical overlapping takes place, and here also there is physical overlapping. So the angle between this white color orbitals, which are the hybrid orbitals, is 180 degrees. And the geometry that we say over here, the geometry over here is linear. It is a linear geometry. Have you understood this, madam?
Yes, sir.
Okay. Okay. So now what happens over here is the next diagram or the next hybridization. Have you copied down?
Yes, sir. I copied them.
Okay. So now the next is little difficult, little tricky hybridization, that is of ethine. So ethine is C2H2. Okay. And the structure of ethine, to draw the Lewis structure or the normal structure that we draw in organic, will be something like this. Okay. So obviously carbon will go for hybridization. Carbon's configuration will be 1s2, 2s2, and 2p2. Got it? Now the ground state configuration, you know that carbon will always go in excited state. So you will have ground state, excited state, and then the hybrid orbital. Okay. So let's do this. In the ground state, it will be like 2s2 and 2p2. Okay, then one electron from 2s jumps into 2p, so that carbon will have 4 unpaired electrons because its valency is 4, so it should have 4 unpaired electrons. So the ground state, it's like 1s2, 2s2, and this is like 2p2, 2s2, 2p2. One electron jumps from 2s to 2p, from 2s to 2p. यहाँ पे jump करेगा. Okay, and when it jumps, it will have 4 unpaired electrons. And now if you carefully check, one s orbital overlaps with one p orbital. Okay, to form sp hybridization. It will be sp hybridization. Will be sp hybridization. Because one s orbital is overlapping with one p orbital. Got it? Now they say that the hybrid orbitals, how many hybrid orbitals will be there? You tell me, chalo. How many hybrid orbitals will be there?
2.
2. Very good. Because one s orbital is overlapping with one p orbital. So there will be 2 hybrid orbitals. Okay. If someone is asking you, madam, give me the reason, then you have to tell that, sir, if there are 2 atomic orbitals which are overlapping, there will be 2 hybrid orbitals obtained, because the rule says the number of hybrid orbitals are always equal to number of overlapping atomic orbitals. So there will be 2 hybrid orbitals, and both of them shall have the same name, that is sp. Both the orbitals name will be sp. Both of them will have same energy level. Both of them will have definite orientation. and both of them will have maximum stability, because that is what is all about hybridization. Okay, and both of them will have one unpaired electrons each. So now the geometry is linear because the hybridization is sp. So again draw those sp orbitals. The first orbital, okay, enlarge it. Right, right. Got it. Just do it. So this is the first orbital. Just 1 minute. Huh? Okay. Active. So first orbital will be okay, and two carbon atoms will be formed. Just 1 minute, huh, madam. There will be a sigma bond that will be formed like this. So there is formation of a sigma bond. Okay. So this is the sigma bond between the two carbon atoms. Now, can you tell me how many unhybrid orbitals are there?
Two unhybrid orbitals.
Very good. And do you know that the unhybrid orbitals, they will always form pi bonds? Okay. So carbon shall have two unhybrid orbitals. So this is the first unhybrid orbital. This is the first unhybrid orbital of the second carbon. So now there will be what kind of overlapping between the unhybrid orbitals? There will be a parallel overlap. But there is one more unhybrid orbital for both the carbon atoms, like this, like this. Okay, and see, there will be parallel overlapping. So how many pi bonds are formed? Two pi bonds are formed. Two pi bonds are formed. Got it?
Yes, sir.
Okay. Now there are two hydrogen atoms also. There are two hydrogen atoms. So there are first orbital, second. This will be the first hybrid orbital, and this is the second. And you will have one hydrogen over here. Okay, we'll have one hydrogen over here. Like first hydrogen and second hydrogen. So here there will be a sigma bond, because s orbital always forms sigma bond. So the geometry over here is linear. The bond angle for a linear hybridization, for a linear geometry, is always 180 degrees. It is 180 degrees. Bond angle is 180 degrees. Got it, madam?
Yes, sir.
Are you done with this?
1 second, sir. I'm right now.
Just let me know once you are done.
Done, sir.
Done. Now the next hybridization. So what are the hybridizations that we have done? We have done sp3, sp2, and sp. Okay. Now let's go for the next hybridization. But before going on to the next hybridization, again I will just show you the geometry of acetylene, which we have drawn it on the board. Acetylene is also called ethyne. See, this C2H, remember this, the name of this C2H2 compound is ethyne, or it is also called acetylene. Okay, it is also called acetylene. Okay, so again, I will just stop the screen sharing for some time so that I can show you the shape properly. So if you carefully check over here, see, these are the two carbon atoms. Can you see them? These two carbon atoms. The black color are the carbon atoms. Okay. Now, if you carefully check, see there are three bonds between these two carbon atoms. One above, can you see with a gray color bond over here? This
Yes.
one. And then there are two, purple color bonds. See, two purple color bonds. So in all, between these two carbon atoms, there are three covalent bonds. And in the diagram, where are these three covalent bonds? Then tell them, sir, you look at the diagram properly. Where are these three covalent bonds in our diagram? So if you carefully check, the first bond is this red color bond, which I'm highlighting it again. This bond, because that will be a sigma bond. Correct? The second bond is between the orange color orbitals. There are two orange color orbitals, and then there is a parallel overlapping.
Yes.
And the second bond is between the green color orbitals, which I have shown with a blue color overlapping. So there are bonds between the two carbon atoms. The first bond, that is the red bond. You can say in this case, this bond, gray bond. In our diagram, it will be the red bond. It will be a sigma bond because it is obtained by physical overlapping, head-on overlapping, axial overlapping. Whereas the two other bonds, that is the orange color orbital bonds and the green color orbital bonds, they are pi bonds because they are formed by lateral overlapping. And where are the hydrogen atoms in our diagram? See, these are the two hydrogen atoms. Okay. And where are the hydrogen in the diagram? The yellow color circle ones. So if you carefully check, can you see like a linear shape? See, it is a straight line. All the molecules are in straight. Can you see that? So that is the reason why we say that it is a linear geometry. You understood now why it is a linear geometry, madam?
Yes, sir.
Okay. So this is how we need to understand. Okay, when you actually see the live 3D models now, it helps to understand the concepts at a faster rate, and it stays in our memory for a longer duration. Okay, rather than just by hearting the bond angles and the geometries, when you actually see them, it stays in your memory. Okay, sure. Now the next hybridization that we have to do is of PCl5. PCl5. Okay, PCl5 is phosphorus pentafluoride. Okay, so who will be the central atom over here? Tell me. Who will be the central atom? Who will be the central atom over here?
Central atom is P. Phosphorus.
Correct. Yeah, remember we had done 2 lectures ago that the central atom will be that atom which will be least in number. And then if that criteria is not helping us, then we have to go for least electronegativity. But over here, yes, phosphorus is least in number. Phosphorus atomic number is 15. So its ground state configuration becomes 1s2, 2s2, 2p6, 3s2, and 3p3. 3p3. So what will be the valence shell over here? If you carefully check, the valence shell will be this. This will be our valence shell. 3s2, 3p3 will be our valence shell. Okay. So let's draw the ground state. So ground state will be 3s2 like this. And then 3p3. Something like this. So after ground state comes excited state. And in the excited state, we will see that there will be excitation of electrons. And we have to discuss the reason also why there is excitation of electrons. Okay. See, if you fill the electrons over here, it's like 3s2 and 3p. Okay. Now what happens? How many unpaired electrons are there in the ground state for phosphorus, madam? Look at 3p3. There are only 3 unpaired electrons, correct?
Yes.
But the valence of phosphorus in PCl5 is 5. That means it should have 5 unpaired electrons. So now what is going to happen is one of the electrons from 3s will jump into 3d orbital. And since phosphorus belongs to period 3, it has d orbital present. It has d orbital, whereas nitrogen, which is the second period atom and which is just above phosphorus, it does not have d orbital. So nitrogen cannot expand, cannot have jump of electrons, whereas phosphorus can have. So one electron from 3s jumps into 3d. See, this is like 3s, 3p, and this is like 3d. So one electron has jumped from 3s to 3p. Now, how many unpaired electrons are there? 5. So all 5 of them come together. So what orbitals are overlapping over here? 3s, 3p, and 3d. So what will be the hybridization? Chalo, you tell me what should be the hybridization. Think carefully. What orbitals are overlapping? Based on that, try to give me the hybridization. How many s orbitals are participating, madam?
One is
1.
3p,
P
3,
and 1d.
1d.
So the hybridization will become sp3d, sp3d. And if you carefully check over here, for a sp3d hybridization, if you carefully check, what was the geometry? It was trigonal bipyramidal. See, I have written it over here. No, I have not written it. I have not written it for sp3d. It will be trigonal bipyramidal. I will write it down over here. Don't worry, I will write it down over here. It will be sp3d hybridization. Then the geometry will be trigonal bipyramidal. It will be trigonal bipyramidal. Got it? So just join on the same link again. Okay. I will draw the structure